May I kindly request you to share your screen so that we can view your presentation, sir? Hello.
Yeah, please. I'm doing it. Please wait a little bit.
Yes, sir. Your slides are visible.
Okay.
Um, so I'm going to start. So good evening, everyone, and welcome back to the day three of the International Year of Quantum Technology. After a remarkable morning exploring quantum biological systems, we now turn our focus to the material world, where cutting-edge quantum simulations, electronic structure analysis, and precision sensing are shaping the future of applied science. In our evening sessions, we have the privilege of hearing from two distinguished speakers who are joining us once again to deepen our understanding of these exciting frontiers. To begin, please welcome back Dr. Utpal Sarkar, who returns to take us deeper into the field of quantum materials. Yesterday, he delivered an in depth talk on quantum chemistry for predicting the properties of atomic and molecular systems. He guided us through a comprehensive overview from fundamental atomic models and concepts to advanced simulations or experimental computer experiments designed to replicate the reality. His discussion highlighted how these simulations depend on carefully chosen assumptions, approximations, and simplifications, such as density functional theory, that showcases the power of theoretical models to provide profound chemical insights. Today, Dr. Sarkar will share advanced computational methods and data-driven strategies that build upon these foundations, revolutionizing how we model the predict the properties of next-generation materials with greater accuracy and efficiency. Before we begin, please note that there will be a Q&A sessions after this talk, where you will have the opportunity to ask questions and engage in discussion. Please join me in welcoming Dr. Utpal Sarkar back to the platform. The stage is all yours, Dr. Sarkar.
Thank you, Sadhana, for introducing me. Now we are going to talk on the periodic systems. So let us allow me to share my PPT. Is my PPT visible?
Yes, sir.
Okay. So uh, just wait a minute. Okay. So today we will going to discuss about the quantum chemical characterizations of two-dimensional periodic system. Yesterday, we have discussed the molecular systems, so which is basically most of the chemist peoples are interested in, but for periodic system, it's basically two-dimensional, one-dimensional, or three-dimensional systems. Basically, periodic boundary conditions are applied to these systems, and physics as well as chemistry peoples and material science peoples are interested in this type of systems. So before we going to start for these two-dimensional systems, let's have a look on the efficiency of the transistor, because we will definitely use computers to perform the simulations, and quantum. This is basically my talk is oriented about the quantum chemical characterization. So quantum mechanics has to be applied to these systems, and how do you apply the quantum mechanics here? It's not the analytical form you will get, rather simulations or approximate methods we will use, and that has been discussed in yesterday's talks. So now what we left yesterday is basically we have done some calculations, and then from we have seen that how the nitrogen molecules have been simulated in these 50s, when this is the first time the molecular orbital calculation has been done for N2 molecules, and then there are several progresses. Okay, and after that parallelly the computers whose basic component is transistors, how it regularized is presented in this figure. Okay, so this is the year, and this is the thousands of transistors incorporated in these chips. So here initially it was 4004, and then around 1980s it is 8086, and then the number of transistors is, you see, is 50 or something like that, and then thousands, and then 10,000s, and now it's huge. Okay, so up to you see that the scaling is doubling the number of transistors in every 2 years. Okay, so miniaturizations of these systems of that is transistors, and at the same time the efficiency of the computers are also increasing, and it is basically 2 times faster nowadays in every 2 years. Okay, so that is one great story of this enhancement of the semiconductor industries. And now when we are going to use semiconductor, okay, we need to understand the where we will use this. This can be used in capacitors, in supercapacitors, in batteries, and fuel cells. These are basically the energy storing materials. Nowadays, the whole world is looking to how to create energy alternative energies, and at the same time how to store the energy. Okay, so these are the things where you can store energies, and this graph is basically energy versus power. So Capacitor means you have high power, but low energy is also fine. But in batteries, you see, or in fuel cells, it can deliver high energy, but the power is very less. So in today's talk, we will discuss battery and capacitor as a prototype example. Okay, now in this talk, most of the time we will confine ourselves with the materials that are basically coming from the carbons. Carbon atom possesses an exceptional capability in forming strong covalent bonds with fellow carbon atoms or other elements exhibiting diverse state of hybridizations. These SP, SP2, SP3, etc., and create an extensive range of structures starting from small molecules to even extending to a long polymer chains. And approximately 2 centuries ago, approximately 2 centuries ago, researchers found the presence of carbon atom in biomolecules, in organic molecules, as well as in naturally occurring carbon electrodes like diamond, graphite, etc. And in the year 1985, Corto and his co-worker made a significant discovery by uncovering the existence of the third allotropic form of carbon, that is fullerene. Generally, fullerene is basically a hollow cage structure, and it consists of sp2 hybridized fused hexagons and pentagons built with carbon atoms, and their stability is basically influenced by the isolated pentagon rules, which states that the pentagons are encircled and isolated by the hexagons. Okay, so after that, this pentagon, this structure forms this structural stability of fullerene is basically dependent on the bonding nature of the carbon atoms, and each atom forms a sigma bond with three nearby carbon atoms, and thereby sharing three valence electron with them. The fourth valence electron is a part of the delocalized pi electronic system that extends over the entire surface of the molecule, and that gives you the electrons. Okay, so stability consideration poses a restriction to the structure comprising only 5 and 6 member rings. There are several examples of fullerenes. Fullerene C60 is the first one we have discussed. There are other form also, but this is basically sp2 hybridized mainly. Okay, so when you are considering the smaller fullerenes, that time these pentagonal rules breaks down, and still you will get some stabilized fullerene molecules. Apart from that, we will discuss today the graphene, the other SP, SP2 hybridized, SP3 hybridized, and SP, SP2, SP3 hybridized systems. Here, the fundamental one is the graphene, and then from graphene, if you insert the acetylene linkage, then you will get graphene, graphene 3, and graphene 4. We will come to this structure of these systems. But this is the main sp2 hybridized system, so you will get some sorts of electrons here. You can see, because it is not all these are not sp3 hybridized. Similarly, there are other sp2 hybridized systems. There are sp2 sp3 hybridized systems like t graphene, sde graphene, pentagraphene, and pentagraphene, etc., etc. Now, this is the graphene, and if you insert the acetylene linkage between the two carbon atoms, then three different possibilities mainly come. One is that if you insert acetylene linkage, one third of the acetylene, one third, means there are 6 bonds and alternative bonds are basically broken and acetylene linkage is inserted in these positions. So you will get this gamma graphene. If you put two-third of acetylene linkage, like here, then you will get beta graphene like structure. These structures are different. If you put acetylene linkage in all these carbon bonds, CC carbon bonds, then you will get alpha graphene. Okay, this is basically enlarged version of the graphene where between two carbon atoms you are seeing an acetylene linkage. Okay, out of these three, these alpha graphene and beta graphene don't have any intrinsic band gap. However, this gamma graphene shows some intrinsic band. Uh, yes,
Good.
is it? Is there any problem?
Hello, Sadna, please check who is
No, sir.
speaking. I can't identify from here.
Yes, ma'am.
And tell that person to keep the microphone shut.
Okay, sir. Let me check.
Okay,
Participants are
so
requested to please ensure that your microphone is off as well as your video, please. It's a big size call, so please try to understand.
can you proceed, madam?
Yes, sir, you proceed.
Okay, thank you, madam. So we will mainly focused on this gamma graphene because it is showing intrinsic band gap and can use as a semiconductor. So this is the band structure of graphene, and you see the Dirac-like cone here, so it does not shows any band gap. Alpha graphene also same, beta graphene also same, no band gap. However, in case of gamma graphene, you are seeing a band gap opening at the end point. So this non-zero band gap may opens golden opportunity to use it in electronics, and by varying the chain length, by chain length means here this position, one acetylene linkage, two acetylene linkage, three acetylene linkage, you can modulate the band gap of this system, and that's why graphene is more flexible than graphene. So this graphene family has several potential applications like thermal properties, electronic band properties, mechanical properties. All these properties can be used in different applications. Here are few examples I will show. So possible applications as transistor, because it is basically showing some intrinsic band gap, is spintronics. 3D, when doped with 3D transition metal decorated, then this graphene family and vacancy defected graphene family shows some outstanding properties of spintronic applications such as spin singlet half semiconductivity. It can use as a UV light protector, graphene, pristine graphene. This part I will discuss later as an energy storage material also. So this part I will come also in my talk. Solar cell and in photocatalysis, uh, in detect as an electrode material for lithium and sodium ion batteries. This one we will also discuss, and water desalinations in hydrogen purifications for detection of gas molecules, hydrogen storage material, etc. Okay, so let's see the structure of different types of graphene. Here in this graphene, you have only one acetylene linkage. The bond length for this benzene between the two carbon atoms is 1.42 angstrom. However, the bond between the hexagon and the acetylene linkage is 1.41, and the acetylene linkage is basically 1.232. So you are seeing here that sp and sp2 hybridized carbon atoms are present here. Okay, similarly, if you increase the number of acetylene linkage, some shrinkage of the bonds, and some expansion of the bonds are occurring, and you are getting different types of bonding, and so that nature of bonding can change. That means hybridization is also changing, and that gives rise to different conductivity or semiconducting this band gap. So for this graphene, we'll see how the substitutional doping with Bn can modulate its conducting property, and how this substitutional doping can be characterized by identifying of doping site and the concentration. Doping site as well as concentration. These two things can be identified through quantum chemical calculations for the IR spectra and Raman spectra of this graphite. So when we substitute Bn in graphene, this depending upon the doping site and the dopant concentrations, you can use it as a UV light in two things, in electronics as well as in optoelectronics. We will see these two applications. One, for electronics, we will see how it can be used as an anacapacitor. For optoelectronics, we will see how it can be used as a UV light protector. So these are the basic band structure of pristine. Here, pristine graphene. Here you are seeing the band gap of 0.45 electron volt, and that is situated at the M point. It's a direct band gap semiconductor. And these are the participating carbon atoms. There are several carbon atoms, one in the benzene ring, another in the acetylene linkage. So how, which carbon atoms are basically contributing near the edges of the Fermi level, that you can characterize. You see here that the carbon atoms, both the carbon atoms, means hexagon as well as chain site, both are contributing near the Fermi level. However, in the valence band, at a deeper point, let's say around 3 electron volt, the chain site contributions is much more than the ring site contributions. And you can characterize which particular orbital is basically contributing near the Fermi level, as well as throughout the energy level you are considering. Here it is the pz orbital of the carbon atoms that are basically contributing near the Fermi level. Okay, so this is the band structure for graphene, and then when you are increasing the chain length, graphene and graphene 3 and graphene 4, so it's almost basically increasing. But here we have seen some decrease of band gap. But one interesting point here is that for in for odd number of acetylene linkage present, the band gap is located at the M point. However, for even number of acetylene linkage, the band gap is transferred to the gamma point. Okay, so all these are direct band gap semiconductor, and this is the fat band analysis of different graphene. So you can easily identify the energy range and which particular orbitals px, py, or pz for which carbon atoms are basically contributing near the Fermi level. When we dope graphene by Bn, so there are three possibilities. One, we can dope at the ring site. Ring means hexagonal ring. We can dope, and here we have done it. And you can dope it in the chain site also. So here we have done it, and you can dope Bn throughout the system here. Okay, and then how the band gap changes. You see here when it is doped at the chain site, the band gap is 1.39. However, when doped in the ring site, it is 2.5, and when all these carbon atoms are replaced by Bn, it is 4.1 electron, a huge band gap. Okay, so this material actually is basically insulated, you see. So the band structure, all these cases, you see, is a direct band gap semiconductor, and band gap increases depending upon where you are basically you are making the doping, so doping site, and also on the concentrations, and all these structures are basically non-magnetic. We have done some spin resolved calculations, and that shows there is no spin uh, uh, asymmetry in the band structure. So this is the graphical plot of the what we have already discussed. Now this is the contributing orbitals for the each of these carbon, nitrogen, and sorry, each of these carbon, nitrogen, boron, how it is contributing near the Fermi level. Okay, so this is the carbon's contribution, this is nitrogen's contribution, this is boron's contribution. You see here that these are basically symmetric. These are basically symmetric, means it is basically non-magnetic in nature. Okay, so carbon atoms, when it is Bn at chain site, okay, you have some band gap, and it is basically showing here. There is no density of states here. Okay, now here carbon atom is also in the valence band. Okay, in the valence band, carbon atom is contributing, nitrogen atom is contributing, but nitrogen atom contribution in the valence band is more prominent than in the conduction band. Okay, so these features is telling that whatever the electrons are available, that is basically for the nitrogens. Okay, similarly for other structure also, here you see that the boron's contribution is basically in the conduction band. Okay, and nitrogen is basically in the uh, valence band. Some other, like aluminum nitride and boron nitride sheet we have compared. Okay, so here it is aluminum nitride, boron nitride like sheet we have already discussed. A comparison between these shows that when the lattice constant of aluminum nitride is basically larger than the boron nitride sheet, and Bn and An sheets are basically non-magnetic. Aluminum nitrogen bond length at hexagon is 1.84, which is larger than aluminum nitride bond at graphene like an aluminum nitride sheet. Okay, so you can make the comparisons for aluminum and nitrogen is fixed. That means the lattice structure you can also calculate through the quantum chemical calculations for these periodic systems. We can also do the cohesive energy and stability. The cohesive energy per atom for Bn and aluminum we have calculated, and it is found that the graphene like Bn sheet is more stable than the graphene like aluminum sheet, and Bn bond is stronger than the aluminum nitrogen bonding. So these are the charge density plot. You see here, if you these are not purely covalent bonds. You see, so electrons are localized on the around the nitrogen molecules, and electrons are duplicated in the boron. So this is a little bit polar types of bonds of an ionic characters are present. So Bn bonds have some ionic character with charge accumulation near the nitrogen atom and charge depletion near the boron atom, and charge is mainly transferred from boron to nitrogen or aluminum to nitrogen. And a aluminum nitrates aluminum nitrogen bond is more ionic. You see, is more ionic than you see here, and you see here the depletion of electron around aluminum and boron. If you compare here, a little bit of electrons are situated, but here no. Okay, so aluminum nitride bonds are more ionic character than Bn bond, and charge transferred from aluminum to nitrogen. So how these charge rearrangement are occurring within the bonds, that you can also quantify here. These are the band gap for aluminum nitrate seeds. So if you are interested, you have a look on it. And this PDOS we have already discussed. So the same thing here, but for this particular structure. Okay, now we are going to the another analysis that is called COHP, crystal orbital Hamilton population analysis, which tells you the nature of chemical bonding. Okay, so here you see this we have plotted as minus COHP. Okay, so this is my Fermi level, so this is my valence band, and this is my conduction band, and positive value and negative value you will get. Okay, so depending upon whether it is positive or whether it is negative, you can say that that particular bond is basically antibonding in character or bonding in character. So here BN triple bond we have considered. So it is like this. It is in the valence band. Okay. BN at the hexagon and BN concentrating at the ring. These three we have considered. Okay. And all are basically in the valence band, all are basically contributing. So BN in VB and CV energy states near the Fermi level are in bonding states. You see here, they all are positive. Okay, but for aluminum nitride, you see here. Okay, in the valence band, here it is basically positive, but here you see. Okay, so in the conduction band, these are basically antibonding states. So antibonding in nature. So bonding and antibonding character for this chemical system or any chemical periodic chemical systems, you can also analyze through quantum mechanical calculations. Now, what if if we dope the graphene with single boron atom or with two boron or three boron at the chain and ring side or single nitrogen at chain and ring side, two and three nitrogen atom at chain and ring side. So when we do, this is the calculations for boron doping with different concentrations and at different places, chain or ring. Okay, so lattice vectors changes, and you see here that when BN doping does not gives you any magnetism. However, only boron doping, you see here, boron doping at a chain site gives magnetism here. Okay, so they are magnetic in character. However, boron doping at the ring site does not give rise to any magnetism. Okay, and these are the corresponding cohesive energies. So boron doping at ring site is more preferable than at chain site. If you see the cohesive energies, and boron doping at chain site introduce magnetism. However, for nitrogen doping, you see there is no magnetism here, and so these are basically nitrogen doping are basically non-magnetic in character, and nitrogen doping at chain site is more preferable than the nitrogen doping at the ring site. You see here is basically larger than this. Okay, corresponding one. So this one and this one, this one and this one, and this one with this one. These are the corresponding band structure for boron doping. Okay, so here for single boron doping, you see the asymmetry of the band structures here. So you see for the sum of the bands are crossing the Fermi level here. This is the Fermi level, and this is for one boron, this is at two boron, this is at three boron. Okay, so these are basically crossing the Fermi level. Okay, and it is not located at the gamma and m points. You see. So here is basically boron and nitrogen creates impurity states in the vicinity of the vicinity of the Fermi level and enhances the carrier density by creating additional charge carrier. You see here. Okay. Similarly, nitrogen doping at chain site we have done. Okay, so graphene with one nitrogen doping, you see the whatever these valence, these conduction bands are basically now coming down here in all these cases. Okay, so nitrogen doping at chain site is more preferable than nitrogen doping at ring site. This is coming from the stability analysis or cohesive energy, and nitrogen doping dope graphene are non-magnetic irrespective of the doping site. Now some other structures XY ions we have considered, where X represents boron, aluminium, and gallium. Just wait a minute, I'm taking a glass of water. I'm taking. Please hold on. I'm taking a glass of water. So we have considered here boron, aluminium, and gallium. And for why we have considered nitrogen, phosphorus, and arsen. Okay, so all these XY ions have planar geometry with D3H symmetry and belonging to this hexagonal lattice. Gallium arsenide and gallium phosphide, these two have some additional buckling. You see here, buckling structures, and the structures containing nitrogen, boron, arsenic, these are showing some gradual increase of the bonds depending upon how much the ionic radius it has. Okay, so when I move along this group, so whatever expected from chemical intuitions is basically reflecting in our calculations also. Okay, except buckled structure for these two, in all other systems exhibit planar structure like this. Okay, and it is sp2 hybridized. The CC bond length and of chain gets expanded due to doping at hexagon, but exhibits triple bond characters. Okay, these are all published paper, and whatever we are discussing is discussing from our lab work only. These are the band gap, and these are the formation energy, whether these systems are stable or not, whether এই টপটা চলছে this is the DFT band gap. We have also done this classical band gap, and you see when we enhanced our calculations, the model of calculations, though it is time consuming and computationally expensive, but these quasi-particle band gaps are very close to the experimental results. So we have done for all these materials, and it is basically increasing in nature, but because the DFT calculation, only DFT calculation underestimates the band gap, and it is clearly visible from here. What is interesting here is that what is
No,
interesting.
I think someone's mic is on. Participants are requested to turn off your mic. Please.
So what is interesting here is that the band gap in most of the systems are direct band gap and located at the end point. However, some indirect band gap are also available. Okay, so even if you consider two different formalism, one is DFT, another is GW, then you see that indirect band gap for DFT calculations and it is in between M and gamma points. However, using GW calculations, we are getting direct band gap at the M point only. And these are the case for gallium arsenide and gallium phosphide. Okay, so very interesting. Depending this particular band gap, you can use it for quasi-particle band gaps are basically very close to the experimental one. So you can believe that this, if you synthesize this material, it will show this particular band gap range. And it is this quasi-particle band gap of arsenide is sufficient to overcome the endothermic character of water splitting reactions. And it is greater than basically 1.23 electron volt. And boron phosphide can be expected as an optimal band gap for photocatalyst lies between 2 to 3 electron volt, and our obtained quasi-particle band gap is very close to 2 electron volt. Other optical properties we have done GW along with BSE. So here you see that this is basically uh, 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 for different yes. So
Hello. Apologize for interruption, Dr. Sarkar. So, may I kindly request to all the participants to please keep their microphones muted during the sessions to avoid any background disturbance. Please keep your microphone off. Mr. Ajit Vardi. Hello.
आपके गाड़ी में बोला नहीं मतलब सबके गाड़ी में ऐसे ही हो रहा है
Hello. Hello, Mr. Ajit Vardi. Okay. Okay, sir. You can
okay,
proceed, sir.
so this is basically boron nitride here. Here you see that all these ions, Xn ions, fall in the UV region. Okay, and that means this can be used as a potential UV absorber. And the presence of strong peak, epsilon 2 peak, uh, is near the infrared region estimates the probable applications of boron phosphide. This is basically boron phosphide you see here. Okay, so probable application of this boron phosphide ion and boron arsenide ion in biomedical applications. So these are the band gap, optical band gap with GW, GW plus BSE, and this is the exciton binding energy that we have calculated from here. Okay, so that particular things you can also get is a very high level calculations, though time remaining in and computationally expensive, but at finally you will get a results which you can compare with your experiment. Okay, so this is very interesting one. So inclusion of electron phonon interactions shifted the optical band gap and strong absorption peak you see here. Okay, to visible region of the electromagnetic spectra, indicating that a significant fraction of visible light can be harvested by this substance. Thus, these materials can be very promising for visible light, light-driven photocatalysis. Now, this is the phonon dispersion curve, which shows that all these systems are dynamically stable. And now we'll go how you can use this particular material as a capacitor. So for that, this is one plate of the capacitor. This is another plate of the capacitor. They are separated by some distance. And if you apply electric field, then there are some charges located here. There are some charges located here. You will get some capacitance. So this is when there is no other thing present in between this, then it is basically nano scale capacitors. And if you put the electric medium here to store, because once your electric field is switched off, then this polarization vanishes and then again it returns to its original positions. However, if you put some dielectric medium here, then there is possibility to store the charges which are separated between these two layers. And here, these two layers can be placed in different ways. The most stable one is this one. Another possibility, so it is A stacking, AB stacking, and A alpha, B alpha stacking. Out of this, only this stacking mode is very stable one. So we have whatever we will discuss with this stacking mode. Okay, and we'll dope the system at different positions with different concentrations. Okay, so you can both these layer have same type of doping, then it is homo. If one layer have different number of atoms than the other one, then it is hetero. So Bn at chain, Bn at chain or ring or Bn seat gives you homo Bn derivatives, but Bn at chain and Bn at ring, one position, Bn at ring position is dope. However, for other one at chain side it is dope, or vice versa, or some other combinations, then it is called heterobian derivatives. And for these two different one, this is the stability, how stable they are. So this is the most stable one. However, for this heterobilayer Pistine and BN seat is the most stable one, and this one is the least stable one among this. This is the energy storage on this capacitor. This is the charge storage, and this is the capacitance of this for different electric fields. Okay, so what we have seen is that energy storing capacity for crystalline graphene is large than the other one. The least one is BN and BN layer. This is the charge storage, is also the same nature. You see here, the charge storage is basically non-linear in nature, half kx square type of things. However, here it is basically linearly increasing. This is for negative electric field, this is for positive electric field, and it is more or less basically symmetric, because symmetric structure. Same thing here also, homobilayer, it is symmetric. One interesting thing happens here for heterobilayer, if you consider, then these structures are not basically symmetric, because one layer have different property than the other layer, and depending upon the electric field, some residual amount of electric field or charge, whatever you say, they can reside already, and that overcome the electric field have to overcome or minimize that effect, and that is presented here, and that is why it is not symmetric. Otherwise, the nature of the two are basically same. One thing here is that for peace time you are getting the maxima for all these cases, you see, okay, and the least you are getting for BN layer, okay. So same here. Another one, this is basically for periodic structure. So periodic structure is basically an ideal one, okay. So when you are doing the experiment, when you are synthesizing the material, finally that particular material has some boundary, that means it is ended. So that ended means it is the end of this the end. Here we have functionalized with hydrogen atom. So hydrogen ended graphene system. So it is basically a molecular system with this one is pure graphene and this is the end of graphene. And for this molecular system, we have calculated the same, and this is the homologo gap and binding energy and how much capacitance we have. So here it is. So dipole moment is linearly increasing for this system with increasing electric field, and charge storage between these two is basically increasing. Here it is the energy storage. Energy storage is quadratic in nature, whereas the charge is basically linear, as we have found in the earlier cases. This is the capacitance. Okay. So the application of perpendicular electric field stimulates the amount of charge transfer between the graphene layers, and the dipole moment charge storage on each layer and the energy storage increases with the increasing field, but the nature is different. You see here quadratic, it is linear. The heterostructure have sufficient capacitance value, and above a certain electric field, the capacitance gets saturated. That is clearly visible here initially, because there are no more polarizations to occur. That's why. Another one is carbon allotrope we have considered here. Okay, this is twin graphene, and using how it can be used as a capacitor. So twin graphene structure is this one. So if you see from the top view, it is look like graphene. If you see from the side view, this benzening you see here is this is benzening, this is benzening. Okay, so there are several types of bonding occur, and we have seen the different type of stability, thermal stability, dynamical stability, and mechanical stability also. And this is the phonon band structures and different positions, how the doping changes, and this particular uh, material shows a very high dielectric constant, and this dielectric constant, this very high value of band gap implies that this material can be used as a dielectric medium between the two seat. We can use it as a dielectric medium, and that's why we have taken this one and calculated the electric field versus band gap for these structures. And what we have found is that for AB stacked twin graphene, this is the field and this is the band gap. Band gap is modulating. For this case, we have get direct band gap, but at a particular value of the electric field, you see, now it changes to indirect band gap. Okay, and for this single layer twin graphene like BN sheet sandwiched between pristine twin graphene sheet, in this case, you see, initially you have some band gap, direct band gap, but then when you turn on the electric field, this system turns out to be metallic in nature. Okay. Similarly, here also direct band gap initially and then metallic. Okay. So depending upon your electric field and material, it is not only changing the position of the band gap, the nature of the band gap, value of the band gap, it is changing, is semiconducting to metallic property also. Okay, that you can tune. So this is a very good, interesting thing. So different stacking mode we have considered, and what is the lattice parameter interlayer distance binding energy band gap we have calculated for this structure, and we have inserted this dielectric material here and applied the electric field along these directions and measures the capacitance. Okay, so these are the charges. This is 1 by 1 dielectric medium, 2 dielectric medium, 3 dielectric medium, and so on. So this is, we have not put any dielectric medium, that is only nanoscale capacitor, only separated by 2 electrodes. Okay. And then we put 1 dielectric medium here. This is the red curve. So when we are putting the dielectric medium, the charge storage capacity is decreasing. It is as expected. This is the energy storage capacity. It is the 0 BN, no dielectric, and then we are 1 by 1 increasing the layer, and highest energy storing capacity is observed for 3 BN layer. Among this, capacitance is highest for uh, 0, because that time more it is more polarizable, and if you put the dielectric, then it is less polarizable, and as a result of which you are getting less capacitance here, which is visible here. So the nanoscale dielectric capacitor has these are the nanoscale dielectric capacitor, because we are putting this here. However, this is nanoscale capacitor, no dielectric media. So nanoscale dielectric capacitor has lower capacitance than nanoscale capacitor, and NDC model is generally more advantageous than the nanoscale model for practical interpretation due to low breakdown discharge at the high electric field. So though it is showing less capacitance, but it is useful because you are using dielectric medium in between this. So summary is basically two types of model we have discussed: nanoscale capacitor and nanoscale dielectric capacitor. Nanoscale capacitor capacitance is very large, is 38 or around 40 farad per gram. However, for nanoscale dielectric capacitor is of the order of 1 to 6 farad per gram, and capacitance decreases with the increase of the electric field, and capacitance increases with the increasing electric field. This is the summary of this work. Another work is the same material for electrode, and as a electrode material. So here we have considered, we have checked whether this particular electrode of carbon can be used as a anode material or not. Okay, so so here we have considered differential absorption energy by putting one after another the sodium, magnesium, aluminum, calcium ions, and checked how much it can absorb. Okay, and what is the reaction energy needed to cause one to migrate the electron over the surface? So, two best possible positions where it can absorb is this one and this one, and so these two position can be reached by overcoming this barrier, only this over the top of the CC triple bond, or over the top of the whole hexagon. So this is over the top of the whole hexagon. This path is over the top of this acetylene linkage. So this path is lower, then it can easily go through this path. So sodium is basically migrating through this path. So the just we have calculated the open circuit voltage and theoretical capacitance and diffusion barrier. So twin graphene as a anode material you can use for sodium ion and magnesium ion batteries, and it has low diffusion barrier and moderate OCV than other carbon electrodes. This is for graphene. We have considered and published. Sodium, this is for sodium. This is another pentagraphene. We have design this particular structure. It is sp hybridized as well as sp2 hybridized as well as sp3 hybridized carbon atoms present here. Okay. So different types of carbon atoms. This C1, it is sp3 hybridized, 4 carbon atoms nearby. This is basically sp2 hybridized carbons, and these carbons are basically sp hybridized carbons. So a tug of war between all these three different hybridizations is occurring in this particular material. We have characterized this material through molecular dynamics simulations at 300-degree temperatures and phonon band structures, whether this material is stable or not. Some other characterizations we have done, that is like mechanical stability, and we have calculated the Young's modulus, Poisson's ratios, etc., and the coefficients C11, C12, C66. The electronic properties is very interesting. We have for this particular material, we have uh, calculated the mobilities of electrons and holes, and it is found that the electrons and hole mobility is basically very large here for this particular material. And we have done these calculations using hybrid functional HSE, which is time consuming. Okay. This material also show behavior that are very close to anode material. So you can use this material as a anode material for lithium ion or sodium ion batteries. So this is for lithium ion and this is for sodium ion. We have calculated all these simulations and it is published paper. If anybody are interested, they can have a look on this particular paper. Now, another thing is that this graphene, whether it can use as in the bioscience as a drug delivery vehicle. So what we have done here is that we have taken a heavy pyramid molecule and studied its interactions with the graphite. Okay, so the energy gap of the pristine graphene using DFT calculations is 0.427 electron volt and is very close to the previous theoretical results that we have found. And energy gap after the absorption is lowering. That means when it is lowering, its conductivity is increasing. That means by simply measuring the conductivity, that means current or something, then you can sense, it can be used as a sensor for favipiravir molecule by changing the, by analyzing the conductivity of the whole system. And this decreased band gap after absorption of primary increases the electrical conductivity because band gap is lowering. So e to the power minus e by kt. So it is proportional to this. So basically your conductivity is basically decreasing electrical conductivity. How this is basically released after absorption, how we can, it can be released to the body, that you can also we have also done some calculations and we have found that with a different pH medium also we have done. Okay, so uh, for the time taken for desorption of the molecule in this particular system is uh, 1 point for non-acidic medium it is 1.42 into 10 to the power 4, but if you use this very large 10 to the power 12 second, right, in non-acidic medium. However, if you do the same thing in acidic medium, then you see the time for desorption is 11 or 12 picosecond. It's very quick. So how quickly the desorption of the molecule from the absorbent surface has taken place with, by changing the pH, you can estimate from these calculations. That is very good example of using the quantum chemical calculations in biological systems. One per prototype. There are several actually, numerous. Now, some other source of calculations is thermoelectric device. You see, this is Nafine structure, and we have calculated the Seebeck coefficients, how this Seebeck coefficient changes with respect to temperature, and that you can also calculate here. So here is the device. This is the left electrode. This is the right electrode of this Nafine, and it is the scattering region. Okay, so this is one end is basically hot, another one end is cold, and if hot and cold end is basically connected, then it will develop some voltage. Okay, so you will get some Seebeck coefficient. That Seebeck coefficient at particular temperature we have calculated, and we have found the Seebeck coefficient at 200 degree Kelvin is greater than 300, 500, and 700, and these are the scale values. So thermoelectric properties of Nafine are highly dependent on parameters like bias voltage, how much bias you are giving, and where the Fermi level is, and what is the temperature at which you are measuring. Okay, so you have find the JT value of this particular material is 0.16 at 200 degree Kelvin temperature, and at room temperature it is basically 0.14, suggesting that this Nafine could be beneficial in the development of thermoelectric material. Now, the final example of quantum mechanics is nowadays everybody is using this data driving approach or machine learning approach. Okay, so what is machine learning? Is basically you have some phenomena. Let's say consider this boat here. Okay, and this is the human. Okay, he is trying this robot to make understand that this is basically robot. This is the learning process. So human being is giving giving lessons or training to the machine, these robots, to learn what these human beings want the machine to learn. Okay, so this is what the aim of this, and then once they learn it, then they can identify, they can do what using this, whatever the information stored in these machines, we can use it for our purpose. So the last year Nobel Prize in physics goes to these two fellows, John Hopfield and Geoffrey Hilton, for their discovery in machine learning or AI, whatever you say, basically recreating the brain. So this is basically the human brain, where we learn uh, through this neural network, and this neural network is actually comprises of neuron and synapses. Okay, and then this neuron is collecting the informations and passes these informations through synapses, and then we'll learn something through this. If this bonding is very strong, then we learn something. If this bonding is not very strong, then we are not able to learn that particular thing. The same thing also is doing by the machine learning. So in artificial neural network interconnected by the nodes, uh, okay, if these are connected with very stronger, this connection is very stronger, then it's okay, fine, then the model works very good. If it is weaker, okay, then it's not a very good learning process. So that is the main funda of this machine learning algorithm. Why we use this one? Because there are challenges in simulations and in experiments. Okay, so choosing or identifying material showing optimal properties for applications. We have huge number of materials with different characteristics and so on and so forth. Among these millions and millions of materials with different compositions, with different environment, they show different properties. So I want to find a material with this particular characterization. How do I choose it? Okay, how do I optimize it? Rather, the problem is more interesting when we are going to optimize this. Okay, so one simple way is that, okay, you will basically search the whole space, but searching will not be very convenient for this huge material, because searching is one-to-one correspondence, whether it is this one or not. But in machine learning, it can give you close results that is not exactly you are suppose trying to get one two high values, and in your data set it is not there, but close to that values, one high value, one low value, one high value, another middle value, and so on and so forth. So By optimizing all these situations, it will give something. So that is why it is very much important, apart from some other one also. So for big molecules, for very large systems, it is basically impossible to do the simulations, quantum mechanical simulations, considering all degrees of freedom, spins, and all those things, relativistic effects. That is basically a nightmare. But using machine learning, if you have already some data set, and if you clever enough to use that data set, and with some moderate number of calculations, you can predict the properties depending upon your problem, of course. So experiments are, on the other hand, is very expensive and time consuming. Similarly, high level accurate calculations is also not feasible because of the limitation of times and computational powers. Only problematic thing is here is that the requirement of significant domain expertise for that. So if you have this one, then this problem can be overcome through machine learning uh, algorithms. So another example is that, suppose this is dog, this is cat, and this is horse. I want to learn, machine wants to learn. So how machine can learn it? Through some particular characteristics. We have to give machine to those particular characteristics. So when we are showing this particular thing, whether it has nose, big nose, the area is black or not, some sorts of characteristics we are giving, and if it matches with that, then the machine can identify it is basically a dog. So here for dog, if it has long R, black nose, then it is dog. So if in your data set some pictures has this one, then machine can identify this is basically the dog. Okay, and whether it is dog or cat, they make the comparison. For cat also, they have some characteristics. Okay, and then they compare it, and then they finally come out with some conclusions, decision, basically here. So with the advent of this, new era of physics are basically coming, but it is basically a very old one. It started in 1959. Okay, so here is basically a flowchart of how machine learning works. There is some input data, and then from this, whatever the raw data you have in your hand, you prepare this data and analyze this data. Then with this refined data, your model is, you trained your model, and then using this trained model you predict, and then finally, hey, this is the decision making. This is the conclusion of this one. Okay. So take an example. These are several other places where machine learning are basically applied. Now I am showing one simple example of learning use of machine learning in physics. So this is we have done in our lab, band gap prediction of non-metallic crystals through machine learning approach. Okay, so we have some data set in our hand, and then for this data set we have taken some features to characterize those systems, and then for this character, these particular features are basically correlated with the band gap, and then finally the machine learns that learns some model through some model, and then predicted what will be the band gap for these other sets of molecule, but of same nature. Okay, so the performance of the thermoelectric material in thermoelectric applications can be significantly improved using machine learning techniques that accelerates the prediction of band gap for thermoelectric materials, for designing new thermoelectric materials also, which can outperform the conventional use thermoelectric devices due to low abundance and high cost productions. The key challenges here is that complex composition and design. You see, this composition, there are so many number of elements with different positions occurring in the lattice site. So So complexity in compositions and design, it is nearly impossible for all these systems to calculate the band gap theoretically. Manufacturing and process is also very problematic. If I have to synthesize all these systems, it is also very cumbersome and time consuming, as well as a monetary problem is also there. High cost raw material, lack of standardized testing and evaluations. These are the problems, and that's why we are using machine learning. So this is basically the heat map of all these materials considered, and it is correlated with the band gap. And this red data means implies that it is highly correlated. Correlation here means that which particular characteristics or features of this particular material is highly responsible or highly correlated with the band gap. That we are identified here. And those related features, if I use in our model, then this model can predict the thermoelectric performance or band gap of these systems, right? So that is basically a correlation study, and with these correlations, we are basically using. So here, different machine learning regressions we have used. This first one is multilinear regression, polynomial regression, random forest, and support vector, and nonlinear SVR we have done. And these are the correlation matrix. Is basically, you see R square is 0.85, zero point 0.9, and here 0.82. For SVR, you see it is zero point 0.9, very high value, very high value. Okay, so and this particular graph shows the feature importance, means which particular feature is most important in predicting the band gap. It is identified as the Seebeck coefficients at particular PT, and then particular n means n type at a particular so hole concentration, electron concentration at a particular temperature, the Seebeck coefficients. These are basically the main features that characterize what will be the band gap of that system. So we have done this filtering of these 21,000 of entries whose band gap lies in between this, and this is the simulation procedure, and then ultimately a band gap between 1.1 to 4 electron volt we have considered for these particular materials. And then we have learned enhanced performance. So other properties which are basically very large high band gap that we have discarded, and we have get improved curve for this. You see here the regression is 0.97, 97%. Previously it was 91%. Here it was 83% for Rena forest. Now it is 0.97%, and so on and so forth. So we redefined our dataset. And so the conclusion, this study is showcasing how, with the help of Seebeck coefficient, band gap can be predicted, and the highest performance is observed for random forest algorithm, reflecting the nature of relationship, yielding R squared is 97%, and our study gives an indication of relative importance of the features towards the depicted property. Here it is the band gap. Okay. Another one is since we are discussing about the quantum chemistry, so chemical reactivity is obviously coming. So how the we can predict the chemical reactivity via data-driven approach. So we have taken a big data set, and then through machine learning calculations, we have predicted the chemical reactivity like chemical potential, chemical hardness, electrophilicy. These were all we have yesterday discussed from the DFT point of view. Now, this same thing we are basically predicting without DFT calculations, but through machine learning algorithm. So, through correlation study between the input and output features, we predicted the chemical reactivity parameters, and predicted results using machine learning models are highly correlated with the DFT derived data, and this work speculates the reactivity parameters with very cheap cost and enrich the knowledge of chemical reactivity parameters. And this is the prediction. You see, homolomo is 75% using different different models. Here, 75% or more or less 75% for homolomo. Here, the overall performance across the models. Okay, so R square value for our random forest, for GB, for XGB, and for XBR homolomo prediction is this one, is around 74 or 80%. Ionization potential is around 80%. However, electron affinity is more than 80% electron affinity chemical potential and electrophilicity index, and these are the values for the other models also. Okay, and these are the important features actually for predicting that one. So, what are the important features? You see here, the surface features are basically more crucial to predict the energy band gap between the homos and nomos. Okay, and for electron affinity, you see here it is VSA and E state 1, and what is the position of the nitro group, etc., etc. So these are for chemical potential, and this is for chemical hardness. Okay, so different you see here and here changes. For chemical hardness, important features is log P value. However, for electron affinity is surface features. Okay, so different input features dominates different properties, and that can be identified through machine learning. So this is the conclusions, and now I would like to thank our PhD students. Past PhD student first is Vedamani Singh, Dr. Pegu, Dr. Bornali Bhattacharya, Rajkumar Mondal, Jyotirmoy Dev, and Devolina. So this first Devolina done some calculations on fullerene, Jyotirmoy, Rajkumar, Bornali, and Vedamani. They have done the most of the calculations today. We have shown, and Nirmal has done some calculation thermoelectric material along with Harkishan, and Sadhana is doing some machine learning calculations. Borsa is started. We have used quantum ATK, quantum express, or CS the calculations in most of the time because it is periodic calculations. Yesterday we have discussed the results for Gaussian. Today we have discussed the results of CS, the quantum espresso, and quantum ATK. This is my small machine study you have seen, and whatever we have learned is learned from Professor Chaturaj Ayers. They are my teachers and my collaborators, Nicola, Bommanando, Sandeep, and Hatep. And most of the periodic calculations we have done with my students. So our learning resource is basically my PhD students. And I would like to thank my PhD students. And finally, the funding agency, DST Serve and DA. Thank you.
Thank